Hi, in this video I'm going to carry out the last section of the lab, which is section 2.5 in your lab 1 handout. So, as I mentioned at the end of the previous video, we're going to use our waveform generator to generate a sine wave of various frequencies, and we'll start with 50 Hz and 10 volts peak to peak. So, to do that, let's first set our oscilloscope settings. We're going to use 10 milliseconds per division. 1 millisecond per division is way too short. We're going to have 2 volts per division on each one of these channels. 2 volts per division there, 2 volts per division there, because you have to think we have a 10 volt peak to peak sine wave, so we need to adjust these voltage divisions. Okay, following condition, source channel 1. Now, in this case, because it's a sinusoid, so we have positive and negative voltages, we can use a trigger voltage of 0 volts. And the reason that is because we don't know whether it's going to start negative or positive, so this way it'll cover both scenarios. Now let's head back over to our waveform generator, and to generate a sine wave, we're not going to have to do anything complicated like we did in the last part. We can just use a simple type, change this to sine, and right here we have the options for changing the frequency, amplitude, period, offset. So change the frequency to 50 Hz, which is what's in your lab manual, and the amplitude should be 5 volts, which corresponds to 10 volt peak to peak. The offset should be 0 volts, and the symmetry should be 50%. Now let's head over to our oscilloscope window and press single. Now let's look at this. We have our yellow input sine wave. That's our input waveform. And then, as we can see, the output waveform is another sinusoid of exactly the same frequency as the input, just with a certain phase shift and a certain amplitude difference. So this is exactly what we expect from our frequency response function. So, since we're happy with the results, let's head over to export. Under image, save the image, and then under data, save the CSV data. Alright, now we're going to do the same thing, but with a different frequency sine wave. Now, before we change the frequency of the sine wave and measure different output, we need to measure the peak-to-peak voltage of each one of these two signals, and then the time delay in between them. Because what you're going to do is you're going to take the ratio of the two peak-to-peak voltages. That's going to be the magnitude of the frequency response function a to j omega for omega equals 50 Hz, and you're going to measure the time delay in between these two signals, and from that time delay you can calculate the phase difference, which is the phase of a to j omega when omega equals 50 Hz. So, to measure the peak-to-peak voltage of each one of these two sinusoids, head over to measurements. Now you'll note that there's two measurements menus. It's the first one. Click add, define measurement, vertical, peak to peak for channel 1, and then click channel 2, peak to peak, add, close. And now you see it populated in the table the peak to peak voltages of the input and output waveforms. Make sure you record these before you move on to the next part of the lab. Now, to measure the time delay, actually there's two ways that can be done. One way is we can use X cursors. So we can put an X cursor at position 0. We can look at where each one of these two waveforms intersects the time axis, and then look at the difference there. So, this is at 0 milliseconds, and I'm going to add a second cursor, and I'm going to move that to where this waveform intersects the time axis. Once I have these set up, I can zoom back out, and I can change the reference of the second cursor to be 1. And I think you have to wait for a few seconds. It should populate all the values in this table. Okay. So as you can see, it populated all these different values, delta x, 1 over delta x, etc. The only one we care about is this delta x measurement, which is the time delay between these two waveforms, and it turns out to be around 1 millisecond. So, from this time delay delta x, you can record the phase shift, because how you can do that is you can look at this time delay, what portion of the entire period it is, and then multiply that by 360 degrees, or 2 pi radians. So take this time delay of 1 millisecond, or whatever value you recorded, and divide that by the total period, which is going to be 1 over 50 hertz, so 1 over 50. And then multiply that ratio by 360 degrees to get the phase shift in degrees, or 2 pi radians to get the phase shift in radians. And record that in the table in your lab handout before moving on to the next part of the lab. Alright, so we finished with this first part here. Now let's change the frequency to 200 hertz. So let's head back over to the waveform generator, change the frequency to 200 hertz. Let's go back to our oscilloscope, press single. Now, if this looks a little too crowded, you can adjust the time divisions and voltage divisions accordingly in order to make the graph look better. Over here, I can try 7.5 milliseconds per division. I think that looks good. In any case, you'll see that these peak-to-peak measurements automatically adjust, so there's nothing need to be done there. And for these x-curses, now I have to readjust them to be in the correct positions. So this should be here. Now I'll first have to turn off the reference and move the second x cursor to be there. And you can see that the time delay is around 650 microseconds. Now, just something to note is that what you should see as you keep doing each of the different frequencies is that as you increase the frequency of the input, that the amplitude of the output wave continues to decrease, and the time delay also continues to decrease. Now, that might be counterintuitive, because the phase shift in degrees, as you should have found in your pre-lab, the phase shift increases as you increase the frequency. Now, the reason why the time delay increases is because even though the time delay is decreasing, this time delay over the actual period, because you have to keep in mind the period also decreases. So if you look at the ratio of the time delay over the period, that continuously increases, which is why the phase shift increases. So this looks good. I'm happy with the output. So let's head over to Export, Image, and then click Save. And to save CSV data, press Save. We have 3 more frequencies to do: 500 Hz, 1 kHz, and 5 kHz. So let's get those done. Here's 500 Hz. Let's head back over to our oscilloscope plot, press single, and change that to 5. As you can see, the amplitude decreased, which is what we expect. Let me put these in the right positions. The second x cursor should correspond to the position where the output waveform intersects the t-axis. I put this reference here. As we can see, it's around 350 microseconds. And as we saw in the previous measurement, these peak-to-peak values are adjusted automatically, so nothing else to do there. So let's press Export. Under Image, click Save, and then under Data, click Save to save the CSV data. Now we only have 1 kHz and 5 kHz left in this part of the lab. So same thing like before: 1 kHz, head over to our oscilloscope, press single. I'm going to change this to maybe 2 milliseconds per division. Okay, the peak-to-peak adjusts automatically. I'm going to have to change these references. I'll leave that there, move that there. And now you see I get approximately 200 microseconds. So, if we're happy with the results here, let's head over to Export, save the image data by clicking the Image tab and then Save, and to save CSV data, head over to the Data tab and click Save. Alright, now our last frequency is 5 kHz. This is the highest frequency, so we expect the lowest amplitude and also the lowest time delay, even though the phase shift should be the largest. Head back over here to single. I'm going to have to change the time division. Even 1 millisecond per division is too big, so I'll do 750 microseconds. And actually, it might be better just to do 500. As you can see here, the amplitude is the lowest. You can see that from these peak-to-peak values that it's only 368 millivolts. Also, that means that the ratio of these two, which corresponds to magnitude of a to j omega, is also going to be the lowest. And if I adjust these x cursors, that corresponds to that. And this corresponds to the intersection of the output waveform with the time axis. Now you can see here it's kind of hard to judge because it's so high frequency. It's hard to judge where the output waveform actually intersects the t-axis. So for this, I'm going to change this division to 1 volt per division, and maybe even to 100 millivolts. So now I can see that it does intersect the t-axis right there. So that will make it a lot easier to find that position. Now, of course, before you save your data, make sure to switch it back to 2 volts per division. We can zoom back out, 500 microseconds per division. And as we can see here, the time delay delta x is 33 microseconds, which is the lowest of all the time delay measurements. So this is what we expect based on theoretical calculations. So let's head over to Export, Image, press Save, and then Save CSV Data, press Save in the Data tab. Alright, so that is it for the in-lab portion of Lab 1. Something that you should keep in mind is that in this lab, there really aren't any issues in terms of noise or in terms of the output not being consistent with pre-lab calculations with theoretical results. So if for some reason like your measurements are way off or are exhibiting different trends than expected based on theory, that means that probably something went wrong. That it's not just an error of noise or something like that. So then I would double check your circuit, and I would double check that you're specifying the right waveform in the WaveGen. In any case, this concludes the in-lab portion of Lab 1. I hope all your results turned out okay. You should have gotten results very similar to the results I obtained here. And that's it for this lab.